The time machines of science fiction offer infinite possibilities. But could time travel ever be science fact?
I don't want to blow your minds here, but time travel is not even remotely science fiction. It is absolute science reality.
Time itself may be something you can bend and stretch. So in some respects, time travel may be every bit as real and every bit as strange as our wildest science fiction fantasies.
By investigating time travel, we're unraveling the deepest mysteries of the cosmos.
Thinking about time travel can teach us a lot about the nature of our universe.
It forces us to take on some of the toughest unanswered questions in all of physics.
The more we learn about how the universe works, the stranger it gets.
In Cambridge, England in 2009,
But he only invited people from the future who could travel back into the past.
Professor Hawking waited and waited.
Unfortunately, no one showed up.
Is this proof that time travel doesn't exist? Well, no, maybe he's just known in the future as having thrown really crappy parties.
A party without guests isn't much of a party. Could time travelers jump back in time and liven things up?
We're all moving into the future. That is, in essence, time travel. You're traveling into the future at 60 seconds per minute. It's kind of a cop-out, though. When you talk about time travel, you want to talk about leapfrogging into the future or going into the past. If we want to go to Stephen Hawking's party, which is now in the past, how do we do that?
One way would be to change our passage through time. According to Albert Einstein, that is possible.
100 years ago, Einstein started a scientific revolution which requires us to let go of our common sense ideas about what space and time are.
So instead of thinking of our universe as a three-dimensional place that just changes over time, we should think of reality as this four-dimensional place called space-time.
If you stop and think about it, all of your observations of time are directly coupled to watching something move in space, right? What is a day really but the rising and the setting of the sun? Or an hour but the motion of a hand on a clock?
The three dimensions of space are linked with one dimension of time, making a four-dimensional space-time continuum. It's good news for wannabe time travelers. It means motion through space is connected to motion through time.
We move through space-time, not space or time. And the way this works is that if I'm standing still and I'm not moving through space very quickly, then I move through time as fast as is possible.
This DeLorean doesn't look like it's moving, but it is. It's moving through time. The car, its driver, and the road it's parked on are all moving through time at the same rate, second by second. When the driver hits the gas, some of that movement through time is converted into movement through space.
As soon as I have motion through space, Some of my intrinsic movement through space-time is now taken up by that motion. As I move faster through space, I move slower through time.
Scientists call this time dilation.
One of the consequences of special relativity is that clocks that are traveling faster actually run slower. And this is not just theory, it's been tested, which is incredible.
You can have two atomic clocks, which are perfectly synchronized. And if you take one and stick it in an airplane and have it move at a few hundred miles an hour relative to the other one, their clocks will now be off. And they'll be off by exactly the amount relativity predicted.
And in Einstein's world, we have to rethink even our most basic assumptions.
Before Einstein, we would go up to people on the street and say, "Excuse me, what is the time?" As if there was such a thing as the time. And then Einstein destroyed all that and said that actually each of us carries our own personal time, and they can run at very different rates.
Because time passes differently for everyone, people will have different opinions about when events happen.
Every human who's ever lived felt like that they're living in this moment that we call now. And every human feels like their now is the now.
But one wonderful thing about the universe is there's no way that it can be the same for everybody. People are traveling at different rates, at different speeds. We're moving through the universe in different ways. And there's no way to define universal now.
And the further up we look, the more noticeable this effect.
We have no trouble asking what is going on in Paris right now, right? But we do have trouble saying what is going on in the Andromeda Galaxy right now, because it's so far away that different observers will count as different things now in the Andromeda Galaxy.
And time dilation has a neat trick. It turns fast-moving units into time travelers. March 27, 2015. Astronaut Scott Kelly traveled to the International Space Station. His year-long mission was to study the effects of spaceflight on the human body. Scott was the perfect candidate because he had an identical twin, Mark, back on Earth.
They did this for a variety of reasons to explore the effects of space travel and weightlessness on the human body using as controlled an experiment as possible.
Gravity wasn't the only difference between the twins. Scott was orbiting Earth at 17,000 miles per hour. So compared to his Earthbound twin, Scott moved forwards through time.
This time travel into the future isn't just an abstract physics concept. Scott, the orbiting twin, literally jumped into the future by a fraction of a second. When Scott finally returned back to Earth, because of his rapid speed, he aged just a little bit slower than his brother, and he was actually younger by a tiny fraction of a second.
17,000 miles per hour is fast, but to jump more than a fraction of a second into the future, Scott needed to go way faster.
What if Scott Kelly had wanted to let the Earth age 1,000 years while he was in orbit for 1 year? How fast would he have had to orbit the Earth to do that? And it turns out he'd have to orbit at almost the speed of light.
To put it in perspective, just how fast that is, the fastest human piloted vehicle in history was Apollo 10 that went at 25,000 miles per hour. You would need to go more than 25,000 times faster than that. That's pretty fast.
In the future, we might try to build a spaceship with advanced propulsion capable of light speed. But the laws of physics won't make it easy.
There's a barrier to how fast you can go, a speed limit. Then that is the speed of light. And this is just a fact. This is known observationally to be true. This was in fact measured in the early 1900s, and it is the reason that Einstein came up with the theory of relativity.
The central tenet of special relativity is the speed of light. Nothing can possibly go faster than the speed of light, and no observer can actually watch light in a vacuum going any other speed. It's always exactly the speed of light.
The speed of light is a fundamental property of our universe.
In a real way, the speed of light is not as simple as just a velocity. It's an intrinsic way the universe is put together. As you move closer and closer to the speed of light, time for you compared to another observer begins to slow down more and more, until incredibly at the speed of light, time doesn't progress at all. And this is one of the most mysterious things about the universe to me. Light is so common, it's all around me right now, but light does not experience time.
If you keep traveling faster and faster and you exceed the speed of light, Einstein's theory of special relativity tells us that your clock slows to a stop, but then begins to tick backwards.
But no matter how advanced your propulsion system is, the universe will never let you travel as fast as the speed of light.
It would take an infinite amount of energy to accelerate something, a car, a marble, a galaxy, whatever, to the speed of light. And so for that reason, we think that the speed of light is itself a truly unbreakable speed.
If you want to take a human-sized spacecraft and accelerate it to 10% of the speed of light, let alone 90% or 99% of the speed of light, it requires more energy than humanity has ever used in its entire existence and probably will ever use in its entire existence.
Jumping forward in time isn't simple, but the physics of the universe make it possible.
Going close to the speed of light slingshots you into the future faster, but it does not take you to the past in any way. It's not a way to go backwards in time and visit anyone's party.
A super-fast time-traveling spaceship can't take us back to Hawking's party. But what about a time machine that exists out in the cosmos? In 2009, Stephen Hawking held a party for time travelers. No one showed up. Could that situation ever change?
So here we are in the future, and we'd really love to go to that party. I heard there's great snacks. How do we get back there?
We know extreme speeds can send us into the future, but the universe has another force that messes with time. Gravity.
Remember that there is only something called space-time, not separate space and time. And what gravity really is a bending of space-time itself.
Think of space-time like a rubber sheet. Massive objects like planets and stars stretch it, bending space and the passage of time.
As you get closer to something with a lot of gravity, time and space are stretched, and that really does mean that time goes more slowly.
It even happens on Earth. Here, time runs more slowly close to the ground.
So what this means is if you live high up in an apartment building, your clock is ticking by slightly more quickly than people living at the bottom of the apartment building. You feel the Earth's gravity slightly differently than they do.
If you live in the top floor of a luxury high-rise in a penthouse, you're actually aging more quickly than someone who lives in the basement.
These time differences are just tiny fractions of a second. But there's a place in the universe where powerful gravitational forces slow time dramatically. A black hole.
A black hole is a region of space where the space is so curved that not even light can escape.
A black hole in many ways is a natural time machine. The closer you get to a black hole, the more into that gravity, the slower time goes.
At the center of the Milky Way sits Sagittarius A star, a supermassive black hole with a mass of 4 million suns. To use this natural time machine, we would have to send a spacecraft. The craft would have to travel vast distances through deep space to reach its target, a journey fraught with peril.
The center of the Milky Way galaxy is one of the strangest, most exotic, and violent places in our galaxy.
That gigantic black hole means the environment is filled with things like lots of turbulence, strong magnetic fields, really intense radiation.
And surrounding the black hole, a searing hot disk of gas.
In the vicinity of a black hole, the gravitational field is really strong. But it's not black, and that's because just outside of it, stuff is trying to get in. What it tends to do is circle around in a disk of material that we call an accretion disk that is incredibly dense and hot, emitting high energy particles. There are winds blowing off of it. It's a very violent place, and this is where all the action is.
This is gas that's swirling in closer and closer to the black hole, heating up to millions of degrees, going close to the speed of light.
It's really difficult on Earth to get material moving that fast. And so the fact that there's so much material in this accretion disk traveling at 30% of the speed of light is really mind-blowing.
The backyard of our monster black hole in the middle of our Milky Way isn't for the faint of heart, for sure.
If the craft survives the journey, the crew will see the massive Sagittarius A star up close for the first time and start to feel its effects.
Once that spacecraft gets near the black hole, strange things will begin to occur.
The mission control would see the astronauts say, "Hello." And the astronauts would hear them answer, "Oh my God, I'm worried about you, is everything okay?" Apparently speaking too fast. And then the astronauts would respond, "Oh, I'm fine."
They would seem to be moving in slow motion.
The crew steers the craft into orbit around the supermassive black hole. Mission control might see the craft orbit every 16 hours. But for the crew, the orbit is far shorter. The immense gravity of Sagittarius A star slows the craft's time relative to mission control.
If you enter a strong gravitational field, like near a black hole, and then you come back, you will have experienced less time than someone who just stayed behind here on Earth. But it never feels strange to you. You always look at your wristwatch and the clock is ticking at exactly the same rate as you would expect. You don't even notice that you're in a gravitational field until you come back and compare your clocks to the people who left behind.
In this way, traveling close to a black hole and then coming back allows you to accelerate your passage through time compared to people who stayed behind. So you're jumping in time. You really are time traveling in that way.
If the gravity outside a black hole accelerates a spacecraft through time, what does the inside do? To find out, the crew sends a manned probe towards the black hole's event horizon.
If you could maintain communication with them, one of the things you would observe is that everything would get reddened, that the light is actually losing energy as it comes out of that gravity of the black hole.
It'll get dimmer and dimmer, and eventually, as it falls right onto that event horizon, it just fades out and freezes.
At the event horizon, the probe appears to freeze in time and fade away. But on board the probe, time doesn't change a bit. The crew plunges into the black hole. Inside, immense gravitational forces might stretch the probe like spaghetti. If the craft survives, the crew pushes on towards the central singularity, a place where the laws of physics fail.
The singularity is a true discontinuity, a causal break in the fabric of space-time itself. And that's a fancy way of saying that we have no idea what happens beneath it.
If a singularity is a break in space-time, could it let us jump through time?
What happens on the inside of a supermassive black hole is all very much in the realm of very advanced theoretical physics. In fact, the singularity at the center of a supermassive black hole, it may be possible to even go through it. There's many interpretations of what it could potentially mean. Parallel universes or time travel.
It could be that space and time gets far more chaotic. Different points in space and time connect to each other in every direction. So at the very heart of a black hole, you indeed may be able to access any point in space or time in the universe.
We can't know for sure if a singularity is a portal through time. What we do know is crossing a black hole's event horizon is a one-way trip.
That's the thing about black holes. You ain't coming out.
To return to the present after visiting Professor Hawking's party, we'll need a different time machine. One that lets us come back. They may exist, but they may also crush anything that enters. In the movies, time travel is as easy as hitting 88 miles per hour or diving into a black hole.
We've seen the concept of time travel into the past very often in movies and in TV. Did they get it right? Did they get it wrong? It's hard to tell.
So the way that we currently understand time travel in a real sense is through either traveling very quickly or through a gravitational field. All of these things will bring you into the future, but not into the past.
Could physics offer a different route to the past? Stars and planets curve space-time. Black holes bend it infinitely. But strange theoretical objects called wormholes could punch right through space-time, connecting two distant points with a tunnel.
So if you think about the fabric of space-time is this giant sheet, and you want to get from one point to the other. What a wormhole will do is that it will provide a bridge between the 2 points, making them next to each other.
Travelers would enter one end of a wormhole and exit in a different place, allowing direct access to faraway locations. And since wormholes connect points in space and time, they could unlock real-life time travel.
There are some solutions to general relativity that allow for a concept of wormholes, where if you entered it and could somehow survive traveling through it, you would exit the wormhole at a time before you actually entered it, right? So this would quite literally be time travel.
Travelers would need to ensure the wormhole's entry point is anchored in the present, while the exit is locked in the past. Turns out, there's a way to do that.
You take two ends of a single wormhole, a tunnel through space-time between them. Now, you take one of those and you speed it up to near the speed of light. It will freeze in time, by time dilation. On the other hand, this end of the wormhole will continue to travel through time. Let's say in the far future, you want to travel back to the point where those wormholes are created. You just enter this end of the wormhole, the one that's been ticking forward in time, and you'll emerge from the frozen wormhole back where you started from.
But the furthest back you could travel is limited.
You wouldn't be able to go back before the moment you created it, right? So you could create this time machine here and now, and then people in the future could come back to the moment you created it.
A wormhole time machine won't let us go back to Hawking's party unless it was created before the party took place. And there's a bigger problem with using wormholes for time travel.
If we found a wormhole and tried to use it to travel backward in time, really the gravitational field would be so strong that it would all just collapse into a black hole.
Of course, you need to survive passage through a wormhole, and to do that, you need to essentially hold open the throat of the wormhole. There's only one way to do that.
To keep the wormhole open requires negative energies. That sounds bad, and it should sound bad. We don't know whether you can make these kinds of negative energies.
People talk about exotic forms of energy that could push apart these wormholes, but we don't know of anything of that sort. The closest we know of is the dark energy that is supposedly accelerating the expansion of the universe.
Dark energy pushes the universe apart, but isn't exotic enough to hold open a wormhole. It doesn't have negative energy. But some scientists hope we'll find something that does.
So first people said weird stuff like that just totally can't exist. But then another kind of weird stuff that we were told couldn't exist, dark energy, turned out to actually exist. So now we're not so quick and fast and loose anymore to just say, oh, are we sure that can't exist?
Someday, we may discover a substance with negative energy, opening up the possibility of wormholes and of traveling backwards through time. But there may be another way to travel to the past by controlling time itself.
Time itself may be something you can bend and stretch. There may even be different versions of time. So in some respects, time travel may be every bit as real and every bit as strange as our wildest science fiction fantasies.
Time travel inspires incredible journeys of science fiction, and traveling to the past would be the ultimate vacation.
If I could time travel into the past, I would love to experience ancient Rome at the height of the Roman Empire.
I would travel 13 billion years in the past, and I would watch our galaxy form.
Well, I can tell you if I were a time traveler, I would love to show up for Stephen Hawking's party. But is this actually possible? Could we ever travel back into the past?
If we could travel back in time, the possibilities would be endless. But backwards time travel also causes mystifying temporal paradoxes.
Even in science fiction, time travel is all about paradoxes. Is it possible that you can influence your own past? And the most simple way of putting this is the grandfather paradox.
Imagine you could go backwards in time and kill your grandfather.
In that case, how could your parents have been born? How could you have ever been born?
But if you were never born, then you didn't exist, how did you kill your grandfather? You just run in circles. It doesn't make any sense. It's logically impossible.
It seems like the laws of the universe will not allow you to travel back in time. But maybe there's a loophole.
There could be a way to travel back in time without creating a paradox, thanks to the way that space and time are linked.
Once you believe in four-dimensional space-time, you begin to conceptualize reality as the whole four-dimensional thing, which you then call the block universe. It's like a four-dimensional block of stuff. The different slices are different moments of time.
In the block universe, the past, present, and future coexist.
If you could step outside of this entire framework and see this block universe, you would see the entire history of the universe from time zero to time infinity sitting in front of you.
From dinosaurs roaming the Earth 150 million years ago, to humans colonizing the solar system hundreds of years in the future, and Hawking's party for time travelers in 2009. In the block universe, all of history exists simultaneously. Astrophysicist Paul Sutter explains.
You can think of the block universe as a film reel, where the past and future already exist. They're just frames on the same film. all the frames already exist. They're just right there, but we experience them in a particular order and in a particular direction based on, a particular turn of the handle.
Just like a handle turning a film reel, time flows from past to future. But since every moment in time exists as a frame somewhere on this reel, then surely we can visit them.
If the idea of the block universe is really true, that makes time travel more understandable and more possible. We just need to find a way to get to different parts of this reel.
To do that, we need to find a way to travel through time. We know planets and black holes curve space-time, but Einstein's equations reveal that really massive objects moving around each other can drag space-time into a loop.
The regions of our universe most likely to harbor the greatest possibility for something crazy like time travel is in the most extreme regions of space-time curvature.
You could imagine a very complicated situation where you had enough mass and it was moving in such a way that you could twist space up on itself.
Theoretical objects called naked singularities could do just that. Like the hearts of two black holes, but stretched out infinitely. Two naked singularities moving close to each other could create a looped path through space-time, called a closed time-like curve.
A closed time-like curve is a very special kind of path through space-time where you have some starting point and you start moving through space-time just like you'd advance in frames in this piece of film. And it just so happens in a closed time-like curve that your ending frame is exactly the same as your beginning frame. So as you move through space, you start moving into your future, but you also move into your own past, and you end up at exactly the same point where you started, both in space and in time, and you've closed the loop.
With closed time-like curves, you may be able to visit your own past by looping space-time. But time traveling in the block universe has a big drawback. You can never alter the past.
If this block universe idea is correct, this movie reel universe that all of time exists all at once, that solves the grandfather paradox. You can't go back in time to kill your grandfather because you haven't. You never will. You never will have done it. You can't do it because it didn't happen.
Time travelers in a block universe can't change history. So since we know no one attended Stephen Hawking's party, no one ever will. By investigating time travel, scientists are unraveling mysteries of our universe. But one question remains unanswered. Why does time seem to run in just one direction?
How is it then that we remember the past but we don't know the future?
This seemingly obvious question turns out to have its explanation in the origin of our universe, shockingly.
The passage of time isn't set in stone. Time can be bent, slowed, even frozen. But our experience of time seems fixed. Time only flows in one direction.
There just is a direction to time, in a way there's not a direction to space. There's no difference between up, down, left, right, forward, backward, but there's still a difference between yesterday and tomorrow.
Why does time seem to run forwards and not backwards?
So many things in our everyday life only make sense in one direction of time. You break an egg, it doesn't suddenly become an egg again. You scramble an egg, it doesn't become whole. There's sort of directions of things.
This arrow of time seems to be linked to the chaos and disorder we see in our day-to-day lives. It's best explained over a coffee.
If I have a mug of coffee, there's only one way for all the little bits and pieces of the mug and the liquid in the coffee to be in this shape, and it's right here in front of me.
The mug is in what's called a highly ordered state.
But if I shove it off the table and it smashes into a million pieces, we'll never see all those pieces and the bits of liquid reassemble into the shape of the mug again.
We know the shattered mug won't reassemble itself. In scientific terms, the disorder, or entropy, of the coffee mug increases, but never decreases.
And across the universe, entropy always increases. Just like across the universe, time flows from past to future.
Everything in the universe is gradually becoming more and more disordered. But why?
We never really think about broken eggs reassembling themselves, and that actually may go all the way back to what the conditions of the Big Bang were like.
13.8 billion years ago, space-time rapidly expanded from a tiny point. In the blink of an eye, the universe was born. This marked the first moment of time.
Our current understanding of the universe is that there was a time zero. There was a moment that the universe came into being, and that is the Big Bang.
The Big Bang seems to have been an incredibly low entropy state. Everything was very ordered, very dense and very hot. So there was really nowhere for entropy to go but to increase from that state.
At time zero, the universe expanded from a highly ordered, dense speck of energy. 380,000 years later, the first atoms formed. Gradually, gas began to clump together.
Something like 200 million years later that the first stars formed, and then those formed into galaxies sometime after that.
As the universe ages and expands, it becomes more and more disordered. Galaxies move further and further apart. In trillions of years, disorder will rule. Star-building gas will run out. No new stars will form. When the last stars die, the universe will become cold and dark.
The accelerated and continual and forever expansion of our universe might make for a frankly depressing end. There will come one day when the very last star in the universe just fizzles out, and that is it.
The Big Bang may explain why time seems to flow in one direction, from the past through the present to the future, right down to the last detail.
The rise of entropy in the universe explains why you can scramble an egg from a whole egg, but it's a little harder to make a whole egg from a scrambled one.
And entropy could be a big problem for wannabe time travelers.
The arrow of time means that things get more chaotic over time. So if you were to go back in time, it breaks that law of entropy.
And is entropy, in fact, the reason why we cannot travel into the past? That is getting back to a part of the universe where the energy itself was different, the level of disorder was different. Maybe this law of entropy requires us to keep moving into the future.
The arrow of time seems to be another nail in the coffin for traveling to the past. But some scientists think there could be a workaround. Time travelers might travel to the past in the quantum realm.
Though in our macroscopic world, we don't experience time travel in both directions, it could be that the quantum realm may allow that to be possible.
And quantum time travel could change everything we know about reality. We experience the flow of time in one direction, forwards. Clock hands never reverse. Broken eggs stay broken, and people only attend a party if they're invited before it takes place. But there is a place in the universe where this arrow of time might run both ways. The subatomic realm ruled by quantum mechanics.
In quantum mechanics, we do know that the subatomic world is a very strange place.
Microscopic particles build everything we see in the universe. Quarks, leptons, and bosons. Tiny building blocks that play by their own rules, the laws of quantum mechanics. In the quantum world, subatomic particles can travel through walls or pop in and out of existence. But the laws of quantum mechanics have an even stranger property. They appear to be reversible.
In quantum mechanics, there's no difference between moving to the future and moving to the past, as far as we currently know in the laws of physics.
In the quantum realm, the arrow of time may break down. In March 2019, Russian scientists put this to the test. Using a quantum computer, they simulated an electron traveling a fraction of a second backwards in time. The team calculated that this backwards motion can spontaneously happen in the real world, though perhaps only once in the 13.8 billion year history of the universe.
On the microscopic level, the laws of physics are time reversal invariant. And so this idea of time travel actually appears in the quantum realm, at least in the mathematical calculations.
If the quantum realm's arrow of time runs forwards and backwards in the real world, quantum particles could offer a new route to Stephen Hawking's party. But it might not be a comfortable ride.
If this idea of quantum time travel is true, then you could go to Stephen Hawking's time travel party, but you'd have to do it one subatomic particle at a time.
There are more particles in the human body than grains of sand on the Earth. So safely deconstructing someone into subatomic particles and then rebuilding them isn't likely. But could quantum particles pave the way to a different kind of time travel? We send information using quantum particles every day. Electrons carry signals inside your computer, and photons carry cell phone signals into space and back. Could we encode information onto a set of particles and send them back in time, perhaps to our younger selves?
If you can just send information back in time, right, that could already make you very, very rich. Just go to next week, send back the stock market prices, and let me know. We have some stuff to talk about.
Sending information to the past to alter the present is a tantalizing idea. Perhaps we could send invites for Hawking's party back to scientists in 2009. But even if that's possible, we may never know if they got the message.
Quantum mechanics throws a monkey wrench into this and suggests that maybe the past can branch into many different futures.
If you have an interaction between two subatomic particles, and there's a probability it'll go one way and a probability it'll go another way, to us observing it, it only seems to go one way. But there's this interpretation of quantum mechanics that says they both happen. You've now created two universes. The timeline is split.
In the quantum world, sending a particle, an invitation to a party, or even a DeLorean back in time could create a new timeline. In the new timeline, Hawking's party might have been packed with partygoers, but we aren't a part of that timeline. Neither is our Stephen Hawking.
You're not time traveling back into your own universe and changing things. You're traveling to another universe at that point of time and changing things from there on forward. And it doesn't matter if you change things then, because in that universe, you don't get born later to go back in time to change things. That happened in another universe. I know this stuff is hard to understand. It's hard to explain, too. Maybe if there are an infinite number of universes, there's an alternate version of me that understands it better. I hope he has more hair.
For now, time travel is still science fiction.
So in my personal view, nothing is going to go backward in time. Particles, information, anything like that. Sometimes you hear reports of something going backward in time or being undone or whatever. It's really nothing more than a fancy version of playing a movie backward.
But perhaps someday scientists will discover a source of exotic matter to prop open a wormhole, or find a way to bend space-time back on itself.
You know, never say never, because what we consider science now would have been considered science fiction or the lunatics of a madman a century ago.
But I'm holding out a little bit of hope. Because very smart people have tried to prove that it's actually impossible and failed. You should never say never.
And along the way, we might learn how the universe works.
Time travel is definitely more science fiction than science fact, but thinking about time travel and trying to understand why it might not be possible is really interesting and can teach us a lot about the nature of our universe.
It's also really fascinating to think about this because it forces us to take on some of the toughest unanswered questions in all of physics, and will ultimately probably lead to a deeper understanding of the very nature of reality.
To take the analogy of Alice in Wonderland, the universe really does keep leading us farther and farther down the rabbit hole.